Okay, so today's topic is decision trees. So a decision tree is what we call it as non-parametric supervised learning method. Supervised learning method because you already know it has labels, y values are already provided, and non-parametric I will explain you in a bit. Okay, so non-parametric versus parametric methods. The difference is in parametric methods you will have fixed number of parameters. Okay, in non-parametric methods the number of parameters grow with the data. Okay, parameters as in then it could be a weight, right? Weight is one parameter. Likewise here the depth of the tree could be one parameter. Okay, so the number of parameters grow with the data in non-parametric methods. An assumption is that in parametric method, so you assume a specific form of a model. For example, if you take linear regression, you assume you are going to solve linear regression by making sure of matrix multiplication. And in matrix multiplication, what you are doing is you just for the equation w into x equals to y you are equating, and x you are sending to the right side. So in the training step you are calculating w by equating it to x inverse and transpose, right, multiplied by y. So that way you are just transposing to the moving it to the right side, calculating the inverses, and that method is a part of OLS, ordinary least squares. Okay, so there is a specific form of the model. What model is going to do, that model already knows. Okay, what calculations it's going to do, that model already knows, that code is already written. So that's why we say there is a specific form of the model. But in non-parametric, there is no strong assumptions about the data, hence there is no specific form. Okay, for example, in a tree it may have root node, it may have child nodes, it may have leaf, or we call it as leaf nodes, right? Root node, leaf nodes. But every time you change the data, those tree structure will change. Okay, or every time you change the way in which you are going to pick the samples, that will change the structure of the tree. So that calculations are not specific. It will not give you the same tree every time you change the data, or every time you shuffle the data you will not get the same tree. So there is no specific form here in non-parametric. Next is parametric trees require less training data. Parametric methods require less training data. Non-parametric methods require more training data. And one example is linear regression, logistic regression. Here decision trees, k nearest neighbors is also non-parametric method. Okay, so based on the number of neighbors you take, you're going to classify the point into certain category. So hence k nearest neighbor also becomes non-parametric. That k number is not known for you, right? So it could be 3, it could be 5, it could be 7. Based on that, the cluster size will form, right? So that's why it's non-parametric. Next is flexible. So this is less flexible. It may overfit or underfit. Okay, parametric methods. Non-parametric methods, they are more flexible generally. Doesn't matter what type of data you provide, they will still try to capture the complex patterns. Okay, next is generally faster. So linear regression, logistic regression is faster, and these decision trees are slower when compared to these linear regression. Next is there is some sort of interpretability in the linear regression model or parametric methods. There is some sort of interpretability. Nothing but linear regression has its own feature importance method that I have not shown you. I will show you in upcoming feature engineering classes. So there is some sort of feature importance explainability provided out of the box for parametric methods. Here also you have that method, but generally it is harder to interpret. That is the problem. Okay, so non-parametric methods can be harder to interpret. as compared to parametric methods. So these are several differences. Now coming back to the actual definition, so trees are non-parametric supervised methods. Okay, so which means we just saw all the differences. Next, to create a model that predicts the value of target variable, okay, so you need data features. Basically what the model, how the model works is it's gonna look at the differences in the data, and basis on that the classification happens. Okay, again some of the disadvantages are they are easier, some of the advantages are sometimes they are trees can be visualized, and you can at each tree split or at each decision made, for each decision made, you can visualize what went into making that decision or how the decision was made. That is, some interpretability is there. Requires little data preparation. Okay, this data trees, decision trees, you can use if your data requires lot of pre-processing steps, but you don't want to do the pre-processing steps. Okay, so you don't need, see, other techniques require data normalization. This does not. Decision trees do not require data normalization. Okay, they and other methods require dummy variables to be created for missing data. Okay, some other variables need to be created. Decision trees don't need that. Okay, and other methods require missing values to be either removed or modified or imputed. Decision trees don't need that. Decision trees can work without you doing proper feature engineering. Okay, simply missing value, if it finds missing value, it will take the missing value as a decision split. Okay, so that way it can make the decision. And some tree and algorithm combinations like random forest or XGBoost, they can support missing values also. Okay, so like this way it doesn't require a lot of feature engineering. Okay, you can pre-processing, you can go ahead and use the existing data. Next is the cost of using the tree, that is predicting the data, is logarithmic. Okay, this is not essentially advantage or disadvantage, but this is just the information. So if you want to use the tree for predicting the data, I will anyway give you all the big O notations for all the algorithms, that is your space complexity and tree memory complexity for all the algorithms. And decision trees exhibit logarithmic complexity, not essentially very bad and not essentially very good. Okay, so take this as a just a information point. They can handle both numerical data and categorical data. So for parametric methods, you have to convert your categorical data into numerical data, but here you don't have to. Okay, so and other techniques are specialized. So basically you can use various, you can use various techniques with decision tree, sorry, not decision tree, the other methods, wherein which you are going to take one variable and make some modifications to that. Okay, but here decision trees, they can work well with that categorical data. For example, what I am essentially referring to is encoding. Okay, so encoding methods, you take one categorical variable and then you do some sort of encoding, convert them into numbers, zeros and ones. Here you don't have to do that, and it can handle multiple output problems. Linear regression essentially is used for binary classification, although you can use multi-class as an option. It may not essentially work well, but here decision tree is not like that. It can work on multi-output problems also. Okay, so other algorithms like MLP, they are classified as black box models. That means they don't they are not easy to be observed what is happening in them, but decision tree is called as white box model. So basically you can observe how the model is making the decision, and this is all happening because of Boolean logic, if then else. Okay, or if else, elif else. So all those things are happening here. Okay, Next is you can validate the statistical tests. That is another good reason. Okay, so that means the model is reliable and it performs well. Even if some of the assumptions of the data are violated, it will still continue to work. Okay, so these are the advantages. Disadvantages are sometimes if you don't control, they can create over complex trees. The tree structure will be so complex, it will take a lot of time for you to visualize and understand, and this process is called as overfitting. Okay, overfitting is nothing but with certain tree depth. Okay, if you don't control the tree depth, the decision tree model is going to create overly complex trees to understand the data until they reach something we call it as pure splits. Okay, I will explain all of that, and this process is called as overfitting. So how do you handle overfitting? Is something called as pruning. Okay, pruning and controlling the max depth. Okay, so these are the two solutions. Pruning means you are going to decide which ones are going to be removed in the decision tree. Some leaf nodes will be cut off. Okay, so that is pruning. We will see all of this and discuss in depth. Another disadvantage is sometimes they can be unstable. Okay, unstable in a sense that if your data changes, your tree will change. That is one typical example of the instability. See, for the same data, if you run linear regression model, you will get same result. You will get the same result, more or less same prediction, same F1 score, same recall, same precision, everything. Each time you run the model on the same data. But decision trees are not like that. Decision trees are, if you shuffle the data, you will get a different tree structure. That is one. And if there is a small variation in the data, even that small variation would cause the tree structure to change and completely different tree will be generated. Okay, so that is the problem, big problem of decision tree. How do we solve it? We combine multiple decision trees, and this process is called as ensembling. Okay, how we combine? Again, that has different types of ensembling like boosting, bagging, stacking, lot of things are there. Okay, next disadvantages. So predictions of decision tree are neither smooth nor continuous. Okay, they don't give you either a tree structure or they are not continuous in nature, nothing but they are not in floating point values, but they are piecewise constant approximations. I will explain what this is. Piecewise constant approximations. Okay, so when you calculate the y prediction, okay, when you do the y prediction, then what happens is there is some sort of piecewise constant approximation that is formed. Okay, something like this. Notice the original data. What decision tree has done is, basis on the rules that it has come up with, it is it has clubbed the data here at this decision. At this decision, again it has clubbed the data. All the data points are clubbed into one category here. Okay, again all the data is clubbed into one group. Nothing but the way how it is doing the splitting. Here one decision it made, so it took all these data points under that decision. Again it went ahead and made one more decision. It combined all these data points into another decision. Again multiple data points combined into one decision. So this way, when you plot it, you will get a stepwise or piecewise. So this is one piece, this is one piece, this is one piece. Piecewise constant behavior is seen. Okay, and that is what we are saying. So it somehow, because it's combining a lot of data points under one decision, it somehow is forming piecewise function. Piecewise approximation is being formed. Okay, and they are not good at extrapolation, inference. Okay, so that is what another problem is. And there is another problem apart from this. So optimal decision tree the problem of learning an optimal decision tree. The best decision tree that can have lesser number of depth still arrive at the solution is called as NP complete. Okay, and the problem with this is you have to use greedy algorithms in order to solve this NP complete problem. Okay, and another problem is if you take any greedy algorithm approach, the problem is they may not guarantee optimal decision tree. Okay, to get optimal decision tree, we have to, that problem is called as NP complete. To solve NP complete, we use greedy algorithm, but greedy algorithms don't essentially guarantee us the globally optimal decision tree. Okay, what they essentially give is local optimal tree, but not global optimal tree. Okay, so again, this is solved by ensembling, by combining multiple decision trees. Because they don't give optimal decision tree, this problem, hence we call each decision tree as a weak learner. Okay, so this was an interview question that was asked to me some time back. Okay, I'm not sure if you remember, I had interviewed for a certain position, no? So previously, I think in the month of November or December. So then this question was asked, why is a decision tree called as a weak learner? It's because we use, in order to arrive at the optimal decision tree, we use greedy algorithms that don't guarantee the global optimal decision tree. Hence, decision tree itself is called as weak learner because it's not optimal, it's not globally optimal. Hence, it's a weak learner. Anyway, it can be mitigated using ensembling methods like stacking, boosting, and various methods are there. Okay, so all those things can be utilized. Next is, there are certain concepts that can't be used, cannot be expressed easily with decision trees. Some problems are XOR parity or multiplexer problem. XOR means, you know the XOR gate, right? You know the OR gate. XOR gate is the not exactly opposite, but XOR gate doesn't allow if the inputs are similar. Okay, so if you have 0 and 0, then it will become, ideally in OR gate what happens, if you have 0 0 you have 0 only, then you have 0 1 you have 1, 1 0 you have 1, and 1 1 you have 0, 1 1 you have 1. But for XOR gate what happens, if the inputs are different it becomes 1, if the inputs are same it becomes 0. That is XOR, right? So that problem cannot be solved using decision tree, and other multiplexer problems can also not be solved using decision trees. Okay, again, sometimes they can create bias trees. Okay, so that's why we recommend the data set to be balanced beforehand for the decision tree. Okay, so these are some of the advantages and disadvantages. Any questions still here? If all would just give me a thumbs up. Okay, all right. Now see, before proceeding, let's look decision trees in action. Okay, let's look at them and understand how they work, so that visually if you learn, then you can better understand what is happening, okay, in the code. So first things first, a decision tree, the very first node, okay, is called as the root node, topmost node. Okay, and whatever the following nodes come, they are called as decision nodes. Okay, a tree can have multiple decision nodes, hierarchical decision nodes, and the last layer of leaves that form, nodes that form, are called as leaf nodes. So they are the final outcome. Okay, they are called as leaf nodes, and the center ones are called as decision nodes, where the certain decision was made, and the top one is the root node. Okay, clear? Very simple. Let's look at this data and see how decision tree is forming the decision here. me refresh this page. Okay, so this is the data. The data is very simple. You see three different trees here: oak tree, cherry tree, apple tree. For apple tree, for cherry tree, they have already measured two different things. They have measured diameter and they have measured height. Okay, for diameter, as you can see, cherry tree's diameter can go from, let's just say these are in foot, okay, or feet. So it can go from 1 feet up until 7.5 or 7 to or up to 7 feet. Let's just assume like that. Okay, up to 7 feet height can go, and the diameter can again go from 1 feet to, sorry, not even 1 feet, 0.1 feet to, it can go up to 0. Let's just say 35 or 0.4, up to 0.45. Let's just say up to 0.45 feet the diameter can go for a cherry tree. So that means we can classify cherry tree with basis on the diameter or basis on the height. But if you classify basis on the height, notice the other data points that are also in the same length, so a lot of misclassifications will happen. So that's why, but if you go with diameter up until here, only these points will be misclassified, these ones. That's why let's go with diameter. Okay, that is one. Second thing is, the same applies for the apple tree also. Notice the diameter. So diameter is defined till here, contained till here. Although there are some misclassification points, you can split like that. And notice for the third tree, oak tree. Oak tree is a good option. So if you go with the diameter, there is very minimal mixing of other data points. Okay, hence the first split, if you click on it, the first split will happen at oak tree. Okay. Okay, the first split happened at diameter greater than again these rules automatically the model comes up with. Okay, these rules are decided by the model. So at first split, all the, notice only 2 or 3 misclassified points are there, rest of them are correctly classified. So at the first split, anything greater than or equal to 0.45 is classified as a oak tree. So that is the first decision tree has made. The second decision, okay, is the same thing that we discussed, the diameter of the cherry tree. So what the model is saying is, if the diameter, for the second thing, height is considered as the factor, not the diameter. So what the model is saying is, if the height is up to certain level, that is in this case 4.88, all those will be classified as cherry tree. Okay, although there are some misclassifications, but they are we are kind of accepting them for now. Third split is basis on the height. Yeah, please. I think that's a mistake, typing mistake, but it is greater than or equal to. Okay, it's a mistake, typing mistake. So greater than or equal to 0.45, that is the first split. And second split, as you can see, diameter is less than or equal to. Here as you can see, correctly they have typed. Okay, less than or equal to 4.88 is your cherry tree, and the third split is happening basis on again diameter. So third split is looking at the diameter. So if certain apple trees, in order to classify apple trees, notice one thing. So even though you are basically the whole aim of this decision tree splitting is to get pure splits. Pure split is nothing but you want to have same type of data in each split. Wow, very minimal. Yes. Yes, yes. Yes, yes. Yes, yes. Absolutely, absolutely. So that is not properly written here. Okay. But I would classify that as, I think in a rush they might have made these mistakes, but that's okay. But we know that is not the case, right? Yeah. I mean, it's a type of human error. Um, but I think they have written it in either in a rush or in a very, how do I put it, just they wanted to explain the concept, maybe that's why they didn't pay attention to the rules themselves. Okay, anyway, so if you see it less than 1 second. Okay, so this I can say, call it as a typing error, because you read here on the left side and compare here. See, while typing they have written correctly. Okay, but while just putting it here, maybe they have forgotten, but that's okay, happens. So same is here, and some more classification. That way we have to understand. Anyway, like you correctly pointed out, the diameter again has to be greater than or equal to 0.32 and less than 0.5. That has also should be considered, and whatever that range is. So next split is happening for the apple tree. In apple tree, ideally the split could have happened here. Okay, split could happen here. That way all the things would have been in under apple. Okay, but that didn't happen. Okay, that didn't happen because the tree is trying to retain everything as pure. It's trying to do pure split. Pure split is nothing but the split where all the data points are belong to the same class. That is what it's trying to do. Although there is one data point which is overlapping this yellow one, but rest of them are green. Okay, that's why the split is done here at this point. So next split is happening here again, like you can see. Don't go with this these things. Okay, but like you can see, again it's classifying this into cherry. Okay, these are also cherry, but there are apples also there, and rest whatever is above is there, these are all apples. So this way the split happens. It may not be perfect, that's what I'm trying to say. It may not always be 100% perfect, but some amount of misclassifications are tolerated. But ultimately you can still use all these rule based tree structures to solve the problems. Okay, classification problems. Okay, so this is how the tree can split the data and form the do the classification. Okay, next, the next question remains. The next question is, how did you come up with this rule? How did you calculate this value? That is the question. We didn't tell explicitly, see, if you change the problem, these values will change. So clearly we didn't tell the decision tree to split here only. Why did you split here is the question. Why did the decision tree split exactly at 0.45? We didn't tell it explicitly, right, to split. So that is where we have to understand the concept of entropy and the concept of information gain in order to understand how the partition happened. Okay, now entropy is nothing but randomness. Okay, the physics definition is entropy is nothing but the chaotic movement of particles. Particles could be atoms or molecules, whatever, in a closed system. Now applying that here, applying that to our data sciences, the definition slightly changes. the definition slightly changes. How it means? See, the entropy means if you have large number of data points, okay, if there is a mix up of certain data points belonging to one class with the data points belonging to another class, then that system would be called as entropy. Okay, entropy is nothing but, if for example this is entropy, here there is one green data point with these cherry ones, this is also entropy, not a pure split. Okay, because there are cherry data points mixed with apple data points. Okay, so this is also entropy because there are green data points mixed with yellow data points. So this is what we are calling as impure splits, not pure splits. Okay, so that is what entropy means. So basically entropy measures the amount of information of some variable or event, specifically when there are mix up of data points. Okay, if there are mix up of data points, then there would be entropy greater than 0. Again, another interview question. Okay, entropy, so deliberately the interviewer will ask, okay, so I have a decision tree in one split, all the, let's just say for this example, let's just say all the oak tree data points are classified correctly such that no other tree data points are mixed up. Tell me what is the entropy of the system. Entropy is 0. Okay, because there is no mix up, it has resulted in the pure split. Okay, and if entropy is greater than 1 if there is a mix up of the particles. Okay, sorry, mix up of the data points. So that is how you measure it. And next is pure split and impure splits. Pure split means any decision that gave you the same data points belonging to one class, that is called as pure split, otherwise it's called as impure split. Okay, now let's just say there are certain events are occurring, P1, P2 up to Pn, then the total entropy of that system is written as negative sum of weighted probabilities. Nothing but the probability of occurrence of this event plus the probability occurrence of this event plus probability of occurrence of this event. But it's a negative weighted sum. After you add all those, then you have to add a negative symbol finally. Okay, they are still sum, P1 into log of P1, so you will calculate all of that, the probability of event into log of probability of event you will calculate. For example, let's just say there are 5 events occurring, 5 data points are coming, first data point into log of first data point probability you have to calculate, and you will sum it up. Finally you will attach a negative symbol. Okay, that's how you calculate the entropy, total entropy of the probabilities. Okay, so now what we are saying is, okay, so with this definition what we are saying is total entropy will be 0 if one of the probabilities are 0, because you are summing it up. Okay, sorry, not one but all. Okay, total entropy will be 0. Okay, only if all but one of the PIs are 0. This one has a value of 1. Okay, anyway, so what we are saying is this H value will become 0 if the probability, because you are summing it up, you are multiplying and summing, right? For example, P1 log 2 of P1 plus P2 log 2 of P2, so that way you are summing it up. So whole thing will become 0 when the probabilities of all the when all the probabilities of all the events will become 0. Okay, one can have probability of 1. Okay, what is log 1? Anybody? See, log 1 is 0. Okay, so that means what we are saying is the entire sum will become 0 either if all the probabilities become 0, or only one event can have probability as 1. Okay, so if you calculate 1 into log 1, let's just say 1 into log 1 is still 0. The one event can occur. One event can occur. I will explain in terms of decision tree, but just bear with me. One event can occur and the probability of occurrence of that event is 100%, and then you take log 1, it becomes 0. Hence the entire term becomes 0. Nothing but in a pure split, take it back to the pure split definition. Nothing but if you have pure split, what we are saying is only one event has occurred at this decision, and that event is only the oak tree has occurred. And for this event, because there are no other events, only oak tree event has occurred, so the probability of occurrence of oak tree is 100%, 1. Okay, so 1 into log of 1 is 0, 1 into 0 is 0, hence the total entropy becomes 0. That is what I said. For pure splits, the entropy will be 0. So this is the question, interview question, like that is what I was referring to. So in a pure split, if the oak tree data points are there, interviewer will simply ask you to trick you, what is the entropy of the system of that particular split? The entropy is 0. How did you get to know? From this formula. So hope this point is clear. Did you understand what we are trying to, what did we just discuss? Okay, all right. Second thing what we are saying is entropy can be maximum when all pi are equal. Okay, nothing but if you have 50% data points, or let's just say there are three trees are there, right? 33% of the data points are from cherry, 33 are from apple, and 33 are from oak tree, then the entropy will be maximum. That is what we are saying. Okay, hence it is called as impure situation, impure split. Third thing we are saying is any change, if you try to equalize the probabilities, equalizing the data points in that split, adding the numbers equally, let's just say 33% of the data was already there, 10 data points, 10 data points, 10 data points. If you try to add 11, 1 additional for all the 3 points, entropy increases. Okay, that is what it is. You can visualize like this. See, this is a very important concept. This concept is something that interviewer will keep on asking you. Okay, no matter which interview I have faced, I can tell you at least 80% of them have asked me this question. Okay, so just understand the concept. You can easily phrase them in your own words and explain to the interviewer. See, 3 data points are belonging to negative class, 3 data points are belonging to another class. Okay, proportion of positive class is on the y-axis, x-axis. What happens to entropy? Pay attention to entropy, pay attention to these classes. If I add one additional data point here, what happened to entropy? It decreased, kept on decreasing if you keep on adding. So, but if I keep on adding back, that means if I add equal number of negative class to positive class, entropy will be maximum. That is what we discussed in this point. Okay. If I add more data points, okay, all data points are done. Maybe if I add more here, or maybe remove this ones. Notice positive class is increasing, negative class is decreasing, entropy is decreasing, and we are approaching pure split. Okay, now this is a pure split. For a pure split, entropy is 0. Okay. And the whole point of using a decision tree is to approach entropy equals to 0. Okay, we want entropy to be 0. Another interview question. So they will ask, well, in an ideal situation, what do you expect? Let's just say you have the most optimal decision tree. What do you expect the entropy to be? Entropy, we want the entropy to be 0. That is the aim. Okay. So this way you can understand. Clear? Is this concept clear? Did you give thumbs up? Okay. All right, yeah, thank you very much. Okay, all right, next concept you have to learn is information gain. Okay, just in the above scenario, you saw how the entropy is being calculated, right? Next, information gain is somewhat, not exactly, but somewhat opposite to entropy. What we are essentially saying is we are gaining the information, okay, as we are decreasing the entropy. Basically what we are saying is more and more pure, as we are approaching the pure splits, we are decreasing the entropy and gaining the information about our data. Okay. Yeah, so basically this process is called as information gain. Information gain is nothing but as you want to decrease the impurity from the decision made, okay, we say we are gaining the information. More information about the data set is being gained. That concept is information gain, and it has a somewhat slightly different data, different formula, but notice this H here. H is the parent entropy. What did the parent, how much entropy did the parent have? That we are calculating. From that, in order to get the information gain, we are subtracting how many child nodes belong to, what is the entropy of the child class versus the number of child class, okay, divided by total number of n. So this formula will give us the information gain. Again, no specific need to remember these formulae, okay, but just understand the concepts, that will be enough. Okay, and this decision trees, they use something called ID3 algorithm. Okay, ID3 algorithm is the classical implementation of a decision tree. So how it works is, first you will calculate the entropy associated with each feature in the data set, and then you will start splitting the data set into subsets, okay, using various features or cutoff values. Now at each step, for each split, you will calculate how much information did you gain. Okay, so nothing but going back to this split, very simple here, very simple to understand as well. So what we are essentially saying is, if I do the split of the diameter at, let's just say 0.8, how much information will I gain? If I do the split at 0.7, how much information will I gain, and what is the entropy? If I do the split at 0.5, how much information will gain? So this way multiple values are tested, and whatever the value that gives us the highest information gain versus entropy, that is taken as a split. Okay, so that is what happens here. For example, see, if I do the split here for first round, okay, notice here, if I do the split here at this level, only these many data points, only the data points that are on the right side are available for me. But notice what is the entropy left, remaining entropy of the data set. There are too many data sets available, there are too many data points available for the same class. Okay, the whole aim is to decrease the entropy and gain the information. Hence you will keep on going to the right until you arrive at the maximum entropy, maximum information gain versus the entropy. At this point, okay, you got the entropy level, okay, again, hence you went ahead little bit more, or maybe little bit more here. Now notice, okay, notice the entropy level here, which is your green line in the below chart. It's 0.889 and information gain is 0.464. okay, now notice information gain is increasing, still increasing. At this point information gain was highest. Did you notice information gain? And the entropy is 0.93. So what the algorithm is doing is, on the entire data it will calculate the entropy. Okay, wherever the entropy was the lowest and information gain was the highest, that will be taken as your splitting point. As you can see here, it is 0.45 is taken as the splitting point, this point. Okay, so this point is taken as the splitting point. That is how you got the first decision at greater than or equal to 0.5. The second split will happen going on. So entropy is still decreasing, information gain is still improving, right? Information gain, okay, here maybe. Okay, this is how. Okay, information gain is decreasing. If I go to the left, look at the black line, see 0.52, 0.525, 0.486, 0.514. Okay, information gain is decreasing, entropy is increasing there. Our aim is to decrease the, entropy rate is increasing. Our aim is to decrease the entropy. Okay, so that's what is happening here. So second split will be done basis on this information. Third split will happen, third split means again what we are looking at is only at diameter level. But if you have, we don't have height level here, but diameter level you have to understand. Third diameter level split will happen at this point, so that way everything is combined into one entire category. So this way, basis on diameter, the data points are being classified. Okay, so I will share the link to this. You can read it through at least once. It will take 5 minutes. Spend 5 minutes so that you can get better understanding. So this way the splits are happening. So it's all a game of entropy and information gain. Okay, so that is what the ID3 algorithm is saying here. For the second step, the data is split such that the information gain is maximized and entropy is minimized, and the total entropy of the child nodes is calculated again, and we want that entropy to be as less as possible. Okay, for whatever the n samples are there, so it's calculated. We take the weighted average, by the way. And next, for the next split, we again identify the partition that will again give us the next maximum information gain. Okay, and basis on that we'll do the splitting. So this process is repeated until no further splits are done. Okay, and recursively this process is done for all the data points until we reach the maximum depth that we have specified. Okay, we specify beforehand only what is the maximum depth. And again, this was the interview question: what is the ideal maximum depth that you should choose? Default value is 10. By default, even if you don't specify, decision tree will take the depth of the splitting as 10, but that is a overkill for most of the problems. Unless you have lot of data, unless you have lot of random data. Okay, then you can use maximum depth as 10, but ideally 6 or 7 splits are more than enough. Okay, and I'm not sure if you know this. There is someone found out while working at Facebook or something that they were building graphs, and it turns out that every other person in the world you already know, okay, with 6 steps. So basically what I'm trying to say is, you might know a person who knows another person who knows another person who knows another person who knows another person, this way 6 times to reach any other person in the world. Basically we are 6 persons away from each other in the world. Okay, that's just how we observe in nature. But anyway, even with experience, we have noticed that 6 to 7 splits are more than enough to arrive at a good, decent decision tree which can do the proper classification with reducing the entropy and maximizing the information gain. Understood? Is this understood concept? Information gain and decision tree. Okay, excellent. Next concept we call it as Gini impurity. Gini impurity is sometimes you can use entropy, okay, for the construction of trees, but there is an alternative method also. Instead of calculating entropy, we can also calculate the impurity. Now, impurity uses something called as a variation of Shannon's entropy. Okay, entropy is nothing but if you are working on a imbalanced data set. Okay, if you notice in all this methodology, because you are counting the number of data points, because you are counting the probabilities of the events. Okay, that is what entropy is measuring, probability, pi into log of pi, which is summed up from I to n, okay, with a negative symbol. So probabilities are being measured. Entropy is measuring the probability of occurrence of that event. At this event, the entropy is, maybe at this point, entropy is the minimum for all these data points. So the point I am trying to make is entropy has a flaw. The flaw is, let's just say there were too many oak data points and there were only very fewer cherry data points. Okay, imagine this data where lot of data points were oak tree. Okay, then what would happen naturally is the split would happen. Let's just say all these data points are oak tree up until this point. Then naturally the split will happen here. Okay, and this would mean that we have gained the maximum information about the data points, and we could easily separate out the data. Okay, but the problem is this may not be the ideal decision tree. Okay, entropy, because it's looking at the probabilities, it is biased towards the maximum occurring data points. The problem will not come in the training part, the problem will come in the prediction part. Okay, this is all the whatever we are discussing is the training part. In training part it is fine, the split will happen here and all these data points are belonging to one class, this will belong to another class. But if you ask it to predict, because it's seen lot of these data points are belonging to one class, it will go on to predict all the new data points into this class only, even though the data points may belong to this class, giving advantage to maximum occurring data points. Okay, so that imbalance is that bias cannot be handled using entropy. Okay, so that's why we say for imbalanced data set entropy is prudent, hence we use another method. Okay, we use something called Gini, which also trains the model faster without using logarithms. Okay, now we have to see how that works. Okay, so before seeing that, okay, I think Gini entropy is not explained here, but I will explain you in my notes. But let's have a look at another way of looking at the decision tree, how the entropy log2 is being used to calculate. Why is log2 being used? Again, it is, although no one has asked me this, but I'm just saying, why is log2 used in the calculation? We are using entropy equals to minus summation of 1 to n, right? P of I into log 2 of P of I. Why is 2 being used there? Why shouldn't I use 3 or 10 or 5 or whatever? It's a common sense. Log 2 is being used because you're doing only 2 splits here. Okay, if you had a tree where you wanted to make multiple decisions, this could be used as a data structure question. Okay, then what would happen is you have to use log 3. If you do 3 splits, you have to use log 3. If you use 4 splits at a time, n splits equal to 4, if you specify, you can use the log 4 there, not log 2. Okay, so that's why we are calculating log 2, because we are doing the split into only 2 different values. So again, another look is how decision tree, how entropy has a entropy works is what we are seeing here. So you have mixed of all the data points. In the first split, basis on the height, you saw the split happened. So 2 different data points have come here and 2 values went here. green points work has been classified with minimal entropy possible. 0.235 is the entropy, and again for this one, so the splitting stops here because the entropy, minimum entropy has been reached. So this is done, this data, this node, decision node has stopped. Next, this decision node goes on to make the classification again. Some data points have spilled, and this one has reached the minimum entropy, so this one stops. This no longer makes the decision. Okay, likewise you can see the splits are happening here. This has reached 0 entropy, this one stops, and this one finally makes certain changes. Okay, so again another split, maximum entropy, this is least entropy. Now what we are saying is, from top to down, okay, we have seen the how decision trees and leaf nodes are making the decisions. Okay, at every leaf node we are trying to make a pure decision. Okay, we are trying to come up with a pure split. As you can see, mostly pure split. Okay, here also mostly pure split. This is impure split. What we, because it has taken so much depth, if we bring new data, okay, it won't generalize well on the unseen data. If we bring new data of cherry trees and oak trees and all these apple trees, it may not generalize well. Okay, that is another problem with this entropy, another problem with decision trees. Why? Because the entropy reached here is high. Okay, so this is what we were discussing. Another small disadvantage, of decision trees, perturbations is nothing but small changes. Okay, small change in the data, minor change in the data may entirely alter the structure of the decision tree. For example, notice here, for this sample, the tree structure has been split, is like this. Okay, but notice this decision value 0.44, here 0.45. Because we have used 0.45, the structure has changed, no? So this first split has happened twice. In the first sample, we got all of that data in the very first split, but here we took two splits in order to get to the same. Hence the decision tree depth increased. Okay. Next sample, you see the value is increased slightly, diameter value is increased slightly, again the tree structure differed. Likewise, if you notice, for multiple changes in the values, multiple decision tree structures have come up. Now this is a problem. Okay, this is a problem. Why? Because every time your data, because data keeps on coming. Okay, data is dynamic, we call it, right? So it keeps changing. All these tree structures that we have already trained may not work well with the unseen data. Okay, so that is where the concept of overfitting comes in. Overfitting means the model has learned the training data well, but on the test data it doesn't perform very well at all. Now how do you handle this decision tree overfitting? We handle it with something called pruning them. Pruning is nothing but, okay, as you are approaching the maximum depth, you are gonna stop creating the new leaves, or you will set up the minimum number of leaves so that the decision tree can make the decision. This process is called as pruning. So you won't allow leaves, okay, with few items, basically. Okay, you are cutting the size of the tree. In other words, that's what it means. You are not letting the tree. See, what is the level of this tree? Here it is 1, level 0, level 1, level 2, level 3. 3 levels. So you are controlling that levels max depth. Okay, that is called as pruning. All right. So this was a good. Any questions still here up until this point? How the decision tree is making the decision or making use of entropy and information gain? Yeah, so that's why we specify the max depth. It will stop functioning only if it certain criteria is met. Either it is done segregating the data into pure splits, that is one condition. Second condition, or it will continue until the max depth is reached. Okay. Third condition would be, let me just execute this and okay, either max depth is reached, okay, and there is one more, 1 second, I'll show you. Minimum sample split, no, minimum weight near max features. Yeah, so either the max leaf nodes are reached. So max leaf nodes means, what are leaf nodes? Leaf nodes are the last end level nodes that have the outcome. If you specify I want to have only 10 max leaf nodes, okay, as soon as it reaches the max 10 leaf nodes, it will stop, for example. Okay, very simple. So in this case, let's just say this is a leaf node, this is a leaf node, leaf node, leaf node. There are 1, 2, 3, 4 leaf nodes, and this is also leaf node. Okay, it holds the outcome 1, 2, 3, 4, 5. 5 leaf nodes are here. How many decision nodes are there? This is a decision node 1, 2, 3, and this is a root node. 3 decision nodes, and this is also making a decision. So ideally you can consider that also as decision, but we call it as root node. So 5 leaf nodes are there. If you specify the max depth as 4, then what will happen? It will make this decision, it will make this decision, it will make this decision. It won't make these two, but rather it will stop. It will give some value here and it will stop. So that way 1, 2, 3, 4 will have reached. So this way also you can control how much decision tree will have to work, how much time it will have to work. Either max depth or max leaf nodes also can be used to control the behavior of the decision tree. Okay. Understood till here? Okay. So if you have understood, I want to stop it here, take a small break. Please come back at 10 a.m. Or 10:05 a.m. Okay. After 10:05 a.m. we'll continue where we left off.